So it's my fantastic pleasure to introduce Swen Jacobs now for his talk. Before we had a talk on machine learning is getting awesomely good at breaking our systems and making our systems less secure. What it's not so good at yet is to make sure that our systems are actually secure and that there are no attacks. And so part of the research area that Sven works in is about giving mathematical guarantees or using mathematical methods to figure out how we can make our systems more provably secure. And he's going to talk about the very long, long road that it takes to actually get there for us today. So let's give him a very warm welcome. Thank you.
Thank you, Cas, for your introduction. It's really a big pleasure to be here. It's something completely different than the previous talk. And I thought it's a special occasion, so I'm going to do something special. So this is also a talk like I've never given a talk before. Let's see how it goes. So, of course, I need to explain what do we mean by guaranteed security, and I'm going to take an approach that I'm going to explain it from my perspective, of course. And first, I want to give you an historical perspective, because I like history, and I thought, why not start with the history of what we now call formal methods and explain to you how that developed and until the point where I come in. The second chapter of the talk will be my career. So what Rebecca had in the beginning, I will have at that point, or something roughly like that. You will also see a significant difference there. And then, if time permits, we're going to talk about research. All right, so the first part of the talk will be a road, starting with this man, Alan Turing, and ending where I come into the picture. So let's get into it. A subjective history of formal methods, so by no means complete and mostly based on the things that are important for our work, so the work in my group today. Or to say it otherwise, these are the giants on whose shoulders we stand on. All right, so Alan Turing. What did Turing do? Turing invented what is today called the Turing machine, a computational model that allows to essentially compute anything that any algorithm can compute. So it's what is nowadays even has a name based on the Turing machine, Turing complete. So if a computing system is Turing complete, it can compute essentially anything. And even further than that, he showed that there is a universal Turing machine. So this Turing machine is just one single machine and can get as an input a description of another Turing machine and then executes what that other Turing machine would execute. So you only need one Turing machine, and depending on what you give it as input, it can compute anything. And that is far ahead of the time, considering that computers looked like this, were very specialized. The hardware was explicitly constructed to do a specific task. And here, essentially, you're saying the Turing machine is a universal hardware, and everything you can make it do anything depending on what input it gets. Yeah, so the Turing machine was also showed also used to show that certain problems are undecidable, meaning that there is no algorithm that can compute that reliably. Okay, and all these things are important for us today and for what came afterwards. So afterwards, in the 1940s, people started developing such universal computers in hardware. So based on the von Neumann architecture depicted here, that is more or less still in use today, you have a computer, here depicted with a control unit and an arithmetic logic unit, and you have a memory, and then everything else, this is your universal machine, and everything else is based on software that you put into, that you let the hardware work on. So now we have the separation of software and hardware in practice that Turing already described. And that, of course, then led to development of programming languages. Software becomes more important than hardware, in some sense at least. because the software makes the hardware do what we want it to do. And there also starts the formalization of programming languages with the Backus-Naur form that is also still in use today as a step to formalizing what is a programming language, what is correct syntax in a programming language, as a first step to correctness of programming languages. Okay, and then this continued. Software became more important over time and more complex also over time. Computers evolved significantly, looked like something we can recognize nowadays. And people figured out it's hard to write software such that it does what it should do, that it's correct and has certain properties that we want it to have. So in 1968, people came together at a conference in Garmisch, actually, and discussed about a new discipline of software engineering, bringing more structure, more discipline into writing programs. But these people couldn't really agree what software engineering should be. On the one hand, there were people that had a management focus. So if you have a large team working on software, you need to manage the team. You need to fix how they communicate. You need to give them some structured way to exchange their experiences, mostly based on best practices and not giving you any guarantees in the end. And this is mostly, Andreas has left now, he would have an opinion on it. This is mostly what we consider software engineering today. But there was another group that said, no, software engineering should be based on mathematics and on logics. It should be a very rigorous development process of software, and we should obtain provable properties afterwards. And they considered this to be software engineering, but in the end they sort of gave up, and this is now known as formal methods. And one of the most vocal protagonists at the time was Edsger Dijkstra, who said famously in his Turing Award lecture, the only effective way to raise the confidence level of a program significantly is to give a convincing proof of its correctness. But one should not first make the program and then prove its correctness. The programmer should let correctness proof and program grow hand in hand. So this shows, this is really, he thought about this as the programming discipline that incorporates the formal reasoning. All right, so another important person in this group was Tony Hoare. And these two were very important from my perspective because they laid the foundations of verifying programs, simple programs in some sense. So there's Floyd-Hoare logic, or sometimes only called Hoare logic, where you can make statements like, if you're in a program state P and you execute a command C, then you will be in a program state Q. So it allows you to reason about program states and commands, and mathematical notation allowing you to reason about the states that you will reach when executing a sequence of commands. So if your program is just a finite sequence of commands, that is enough to prove properties. If you have loops in there, then you need to reason about will the loop even terminate and what will happen in repeated applications of the loops. And for that, Dijkstra introduced reasoning methods over loop invariance and termination arguments. And also both of them worked on structured programming. The idea was you shouldn't just allow anything that, for example, your assembler low-level language allows you to do. In particular, Dijkstra was had a strong opinion of not allowing go-to statements that allow you to jump into any line of your code, but code should be structured, and already the structure of the code should be related to what it is supposed to do. Okay, and that allows you to some extent to reason about correctness of programs, but at the time, proofs were done manually. And that is a problem because if the programs grow larger, of course, manual proofs are cumbersome and at some point will not be feasible anymore. So in parallel to these developments, the field of automated reasoning grew and developed, and for the perspective today, I will just consider it as a tool to automate proofs. You can do more with them, but from this perspective, if you want to prove correctness of programs, automated reasoning allows you to automate some of the reasoning process and in the best case to get proofs completely automatically. So one thing that was very important is reasoning about propositional logic. So you can have formulas like this saying, I know that A or B holds, and I know that if A holds, then C must hold, and if B holds, then D must hold. But I also know that C and D do not hold. So can I give A, B, C, and D truth values, true or false, such that this statement holds? So in this case, it's not possible because either C or D have to be implied, so they cannot both be false. And a SAT solver, propositional SAT solver, can solve these kinds of problems with, let's say at this point, dozens or maybe hundreds of variables automatically based on this DPLL procedure. Also, there was resolution for first order predicate logic. I would also call type checking a automated reasoning method that is important, in particular for security proofs also, less so for what I will present. And then this is a bit difficult to position in time. Binary decision diagrams are a very important tool also to express Boolean functions. They were initially introduced in 1959, but the way we use them with all their features and ways to manipulate them was mostly based on the paper in 1986. So these things now allow you to some extent at least, automate the proof task. So you still try to develop your program with correctness in mind, and you maybe annotate it with certain properties that it should have, and then you can use such techniques or try to use such techniques to prove properties of your program. In another step further, model checking was invented in the 1980s. These are Ed Clark, Alan Emerson, and Joseph Sifakis, who also got a Turing Award for their work. And model checking says, well, if the system that I want to analyze can be represented as a finite state system, then I can completely automatically determine what can happen in there, even on infinite runs of the system. So these are long-running systems that might run infinitely, or, well, at least unbounded long. And yeah, they showed how to do that. And interestingly, even though computers at the time were usually not connected to the internet and didn't have multi-core processors, they already in their work considered parallel programs that are executed by multiple processors at the same time. And this poses a major problem, in particular for something completely automatic like model checking, because as you can see here, this is a very simple program with just 3 states. With an A, you go down, with a B, you go up. And you just have these 3 states, but if you have 2 processes that execute this thing at the same time, now you already have a system with 9 states. And so the state space explodes exponentially with the number of processes, so this quickly becomes unfeasible. And one partial solution for that was integrate BDDs that I mentioned before with model checking. Now you can use BDDs as a symbolic representation of sets of states, and that famously allowed them to do 10 to the 20 states and beyond model checking a bit later in the early 90s. Okay, and then a turning point in practical application of such techniques was the Pentium bug in 1994, which showed hardware vendors, so Intel at the time had to recall like essentially a whole generation of Pentium processors because they had this bug. And Intel and AMD, the two biggest, I think, CPU vendors at the time, afterwards decided, oh, we really have to invest in formal methods to verify our hardware designs. So model checking was one of the things it's well suited to do the hardware model checking. All right, so I mentioned the issue of parallelism. If you have multiple processes executing the same program, or maybe different programs at the same time, the state space explodes. But even going beyond that, you might ask the question, well, what happens if I don't know how many processes execute the program? If it could be an arbitrary number, and I still want correctness guarantees regardless of what the number of processes is. And that question has been considered in the, I think it started in the late 80s and then in the 90s. So what you can do there is, there are essentially two methods. I explained this in a bit more detail because that is what we are actually working on. On the one hand, one option is to do special abstractions that allow you to, so what you're doing is you're reasoning over an infinite family of possible systems depending on how many processes interact with each other. So you need nice abstractions that allow you to talk about instances over the whole family at the same time. That is one option. The other option is cutoff theorems, essentially things where you look at a class of systems and from the beginning make an argument that, well, if I have a certain number, say 4 processes doing something, then I can make an argument that by adding a 5th one, nothing essentially new will happen. It will not lead to completely new behavior. Essentially, the 4 processes that are in there will still behave in the same way, even if there's a 5th or more processes. So that is what a cutoff theorem is. These are essentially the two flavors of reasoning for parameterized verification or parameterized model checking. The thing is, to get such results, usually you have to look at very restricted systems. So what people usually did was you restrict how the processes can communicate with each other. So people looked at networks of processes that communicate by pairwise rendezvous. So always 2 processes get together, do one action. Each of them makes a step in one synchronization step, and then the rest of the system continues after that. Or you have token passing, where you have a fixed number of tokens in your system, and the only way to communicate with another process is by sending some token. And you can only do that, of course, if you have a token. Or you might have a form of synchronous broadcast, where one process sends something and the other processes synchronously react to that immediately and at the same time receive the message. And then you have guarded protocols where processes can look at the state of other processes in the system and can make decisions based on that, either based on does there exist somebody in a certain state, or are all other processes in a certain state. And yeah, people have explored this space of different models and got some partial results for when parameterized model checking, completely automatic verification of these systems is possible. At the same time, in the 90s, when computers started to look like this, we had CD-ROMs. There were also still major leaps in automated reasoning. So I mentioned SAT solving before. The DPLL procedure was already pretty good, but actually there was a significant improvement of this procedure, and now SAT solvers could deal with thousands of variables and could routinely solve these problems that are NP-complete. So in general, you might have an exponentially large search space, but in practice, these methods worked really well. And building on these SAT solvers, then SMT solvers were developed, which means now you can write formulas that include, for example, arithmetic theories. So before I had this formula just with A and B. Now the formula can say, well, X is a variable now that is a number. And if X is smaller than 5 and Y is smaller than 4, and I know variable Z is either smaller than X or smaller than Y, and Z should also be greater than 4. And now, whether that formula is satisfiable or not, whether there exist values for X, Y, and Z to make it true, depends on the theory in which you interpret it. So if these are rational numbers, then you can find values for x, y, and z to make it true. So x might be 4.9 and y is something smaller than 4 and z could be 4.1. But if they're integers, then this actually doesn't have a solution. So S&T solvers incorporate this theory reasoning with propositional logic, so with the reasoning over these Boolean operators, and can now automatically solve very complex logical formulas, and this leads to push-button reasoning. For example, the Hoare logic that we had before can now completely be automated using S&T solvers. Okay, and with that we get into the 2000s. And the last thing that I want to mention here before I come in is software model checking. One important step, so I mentioned before, model checking is for finite state systems. Then we had parameterized model checking for systems composed of finite state processes. But if you're thinking about one process, but that has infinite state space. So if you think about software, data structures might be unbounded. Your even individual variables, depending on whether you think of a bounded bit length or whether it could be unbounded. Even a single variable could already have infinitely many values. So to give you an idea how software model checking works is, or how this abstraction refinement works. So think of this as the state space of your program. This is just, it contains infinitely many states. And you want to model check something in there, whether certain bad things can happen. So model checking doesn't allow you to do that. But what you can do is you can define an abstraction. And now I say, well, every box here is a state. So I can definitely say what happens in these boxes. And now I have some corner cases, some boxes where a part of the box is inside and a part of the box is outside. So my abstraction doesn't tell me, is this a behavior of a program or not? So what you do in abstraction refinement is you try to find a concrete execution of the program that leads you to one of these boxes. And then at that point, you refine your abstraction and you add something to your abstraction that tells you, I can add a line here, and now I get new boxes, and this is now included. And you keep on doing this until either you find your program is correct, or you, until either you find a concrete way in which your program is not correct, or until this refinement stops and you still haven't found a bug in your program. And at that point, you're done and verification is successful. But this refinement might go on forever. And this approach actually was used in practice in industry heavily in the static driver verifier by Microsoft from 2002 onward. Okay. So this is where I come in. Sven goes to academia, or how against all odds I got tenure at CISPA. You might be wondering why against all odds. My point in this chapter will be that many things along the way were up to luck. Good luck and bad luck. So let's start with a bit family background also. You might not, or you do not see it when you look at me, but I'm actually part of a underrepresented minority. Both of my parents were non-academics, so neither of them went to university, and neither did any of my aunts and uncles, and neither did any of my grandparents. My mother was a nurse, my father leads a small construction company, and actually while I was in high school, I sometimes jobbed on construction sites to earn some money. Now, I have some statistics here, only from Germany, and they're in German, that show people from non-academic households compared to people where at least one of the parent is an academic. And it's quite frightening. These are the numbers for Germany. So these are all kids that go to school, essentially. These are people that start studying, depending on whether they're from a non-academic household or an academic household. And then it goes over the bachelor, master's, and the PhD. So already at the point where the PhD happens, I'm 10 times less likely to make it there to that point. And I can confirm from my personal experience, for example, it's also quite stunning, I think, at this point already, that here only 21% go to university, and here it's 3/4. So for me, this was also like already this transition was not, it was essentially a coin toss. Like I was seriously thinking, should I go to university or should I not? And then essentially, if you asked me about my future after school, I would say, yeah, maybe I will study. PhD, I don't know, I haven't even thought about it. And me sometimes leading a research group, I would just have laughed at you. It was so far out of the picture. But as we all know, I went to university. And I showed you in the 2000s, when I also then was at university, there was work on automated reasoning and SAT and S&T solvers, and that's roughly where my work also fell in. So the first is the title of my, no, actually not the title, but the topic of my diploma thesis at the university. And the second is the topic of my PhD thesis. So essentially I was working on first order theorem proving, and then later on during my PhD thesis on local theory extensions, which can be seen as making S&T solvers more powerful, very roughly. Okay, and an interesting observation also that I had about my career up to that point is that actually as the challenges got harder, but I was focusing more on what I was interested in, my grades got better. So my high school diploma actually has an average grade of 2.3. My university diploma was 1.2, and then the PhD thesis was summa cum laude. And just because I still didn't believe that I belong there, that I'm really supposed to do this, I went and wrote a single author CAF paper, which is one of my proudest achievements to this day, because that really doesn't happen often. I checked last year, there was a single author paper at that conference. All right, so it worked out well, but could have gone differently. Also, like picking the university didn't really factor into the decision. Like it was clear if I go study, it would be in Saarbrücken, but not because computer science is a good here, which it is, but because that was just where I was, and so I didn't know about any other universities that might be better. All right, so then I have my PhD, and then again the situation, I didn't really plan for this. I didn't really know what will happen after the PhD. By this point I knew I'm good at doing research, and I would like to keep on doing it. But honestly, I did know almost nothing about the academic system. So I was making it up as I go. I was applying for professorships, but yeah, taking postdocs, first at EPFL and then at TU Graz. And again, the second postdoc in particular was a lucky shot. I happened to end up at TU Graz with Roderick Blum, and that immediately clicked. It was immediately a very positive and a very productive working relationship. And also I was lucky that at that time in Austria there was a big national project on formal methods, including some of the top people at the time, like Armin Biere was in Linz, Helmut Veit at TU Vienna, there were Tom Hansinger and Krishnendu Chatterjee at IST, and Roderick, of course, in TU Graz. And I got to discuss my work with all of them and got a lot of input from them, and that was very important for my career. That was actually, you could say, a turning point of my career, but it was completely by chance. So at that time, well, a bit before that, I started working with Bernd Finkbeiner actually on reactive synthesis. And I continued that and started working on parameterized verification when I was there, and bringing the two together also to do parameterized synthesis. And during that time, I also co-founded the reactive synthesis competition, which was, a major milestone, I would say. So I went and created this competition, and you can see here the winners of the first competition, and actually Ed Clark was there. This is at the Vienna Summer of Logic in 2014, and the winners got Kurt Gödel medals from the Kurt Gödel Society in Vienna, and these were handed over by Ed Clark that I had before on the slide as one of the inventors of model checking. Okay, also during this time I published this book, or actually this happened after I left Graz and was already at Saarland University. I returned to Saarland University with a DFG grant for a two-person research project, financing my own position and my first PhD student at the time. All right, so I didn't have a plan, but somehow it worked out. And then again, but again, like, this was a journey of 7 years, and my project was still running, but somehow it wasn't clear that something new would come up. And again, I got lucky, because there was this thing in Saarbrücken here, next to the university, called CISPA, and it would try to expand to become a Helmholtz Center, and they were looking for people. So I got the chance to be a part of CISPA, and since mid-2018 I'm employed at CISPA. When I started here, I also started another new research direction that we'll talk about later on, and continued working on parameterized verification. So then I was on this tenure track now, and at the beginning of 2020, so let's say April 2020, I was 2 years, not quite 2 years into my tenure track. I had a strong publication record. I was really working hard to get publications out. I just had 2 papers accepted at our top tier conference, CAF. I had finished my habilitation the year before, actually, that I had already started at Saarland University. And my PhD student, the first one, was close to finishing. So I thought I'm in a really good position. And then the rest of this should have been smooth sailing, right? Right? The unluckiest day of my life was the 29th of July in 2020. Just after that conference, CAF, was over, I don't know, two days after that or so, I broke my leg. And when I say broke my leg, you might think, yeah, okay, might take 6 or 8 weeks to get back on track. That's what I thought, at least, when I was lying there. I thought, shit, again, 6 weeks where I can't do sports. Because this was COVID year and we couldn't do sports for some time, or you could only do it at home. So I was wrong. This is what my leg looked like afterwards when I left the hospital again. So it was quite complicated. When I say break my leg, it was shattered into dozens of pieces, my lower leg. So I was in hospital for a full month, had 3 operations. After that, it looked like this. I couldn't walk for 4 months. I had rehab after that, or continuing after that, and was regularly in pain whenever you, if you don't use your leg for 4 months and then you try to use it again, it's really painful. And there was another follow-up operation 2 years later in 2022 with another shorter rehab following that. Why am I saying this? I'm saying this because it turns out that deep theoretical research, sitting there and thinking hard about complicated problems, is terribly hard when you're constantly in pain or regularly in pain. All right, so there was quite a bit of good luck, and then there was quite a bit of bad luck. What I also figured out is afterwards, or at least what happened to me, is that bad luck piles on. So once you're in bad luck, it tends to continue. So when I got back and we started producing research papers again, for some reason, I don't know exactly why, it was much harder to get them accepted. It was much harder to get them into the conferences that we wanted them to get into. So to summarize, these were actually 5 years that were really difficult for me, 2 years that were physically the most challenging of my life, followed by 3 years that were mentally the most challenging, because there was very high pressure to get back on the track that I was on before. Okay, since I'm standing here, everything went well. I was able to acquire external funding, grow my group further. We did some of the most exciting work of my whole career. I'm really convinced of that. And I got tenure at CISPA. So I'm still feeling more lucky than unlucky, but I have a feeling that with a bit more bad luck, it could have also turned out the other way. So yeah, I want to take this moment of my talk, even though it's in the middle more or less, to thank everybody who joined me on this crazy road trip. I'm not going to single out anyone. Everybody who helped me out, anybody who was there for me, anybody who collaborated with me, every nice word was important and helped me finding the way on this winding road. And in case you're wondering about my physical well-being, this was me 4 years after the accident. I am bouldering again, even though it's a bit more difficult than it used to be. Okay, when did we start?
We started 22, so
10 minutes.
we can be a little bit relaxed.
Okay. Yeah, so the rest of the talk is about research. You might have expected more of that, but that's how it is. What did we do along the way? One of my research directions was information flow verification. So it turned out in the 2010s, getting back to the historical perspective, in the 2010s it turned out that actually it's the idea of separating software from hardware is nice, and then only having to verify the software because you have some formal model of how a program should behave. But actually for some properties that is not good enough. The Spectre attacks showed this, where an attacker could observe or could use what is happening in the hardware with different cache levels and with speculative execution that is done by modern processors to exploit behavior that cannot be seen if you only look at the abstract software level. So the attacker can exploit what is happening in the hardware, and therefore if you want to verify such a thing or the absence of such attacks, you need to consider the software and at least some aspects of the hardware. And there were models, observational models for cache-based timing attacks like Spectre, but not with speculative execution. So one line of research that we did was extending software model checking that I mentioned before with a representation of speculative execution and an observational model to be able to verify information flow security in presence of these cache side channels. And we developed an approach that can detect such vulnerabilities in code snippets from the Spectre literature. I will not go over the details of the examples since we don't have much time. We later extended the approach to a tool called CureSpec, which can repair vulnerable programs. So it can automatically insert speculation fences that prevent the program from speculating, and therefore these attacks will become impossible. And yeah, we evaluate this on open source libraries with security critical code, and measured also the impact of adding these fences. So we, in contrast to existing mitigations, this is a guided approach that inserts fences where they are really needed. And we measured the impact and the impact of these additional fences on runtime of the repaired programs is then something between 2 and 70%. And then assuming that the observational model that we based it on is correct, the repaired code will be guaranteed to be secure against this type of attacks. Now I marked assuming in red because it's not always clear whether these observational models are correct for the given hardware. So another project that we did was validation of such models against actual hardware. So you start with an observational model, and that and you generate test cases that the model tells you should not be distinguishable by an attacker, and you test whether they really are indistinguishable, or whether an attacker could exploit differences in the cache state after executing two different inputs to get information about your secrets. So again, I will not go over the details. Essentially, you use a formal model of the hardware that you're running on and the programming language to synthesize a relation of inputs that should be, and a code snippet that you generate, to synthesize inputs that should be indistinguishable to an attacker, and then you measure on the actual hardware after executing the code with these inputs, is the cache state different or not? And in that way, we showed that this approach can invalidate models that are expected to be invalid. That is a good sanity check. It also invalidates models that were expected to be valid, pointing to one of two things. Either the model is incorrect, or well, the other way around. Either the documentation of the processor that we used is incomplete, and there's processor behavior that is not documented, and therefore, even if the model is correct with respect to documentation, it will be wrong with respect to the hardware, or the model is wrong even though the documentation is correct. Yeah, and we're also able to detect bugs in the existing formalization of the processor we're using. This is in a interactive theorem prover, a formalization of the ARM v8 that we ran it on, and even there we also found bugs. Okay, that was the new research line that I started after joining CISPA, and we also continued, and the bulk of our work is in parameterized verification of distributed systems. So let me very quickly summarize it. I think this line of research is nowadays even more important than in the 90s when people first started looking at it. Because nowadays, really everything is parallelized, is running in the cloud. We have blockchain, we have these cloud computing in AWS or Cloudflare, where if the system goes down, the economic cost, even if it's not a classical safety critical system, the economic cost is just huge. So the question is more relevant than ever: how can we get correctness guarantees regardless of the number of participants in a protocol, in a network? And we do this in we did this in three different directions. One of them is low level, where you need to be fault tolerant. Then a high level, where you can model applications, assuming that you have low level fault tolerant primitives. And then a third, often neglected direction is including timing properties. So, yeah. Fault tolerant essentially means if you have a big system, things go wrong. Just hardware might not work. if you have sufficiently many different pieces of hardware running over a long time, just there will be hardware faults. But also, fault tolerance can mean there might be attackers in your system. Some of the processes that you're communicating with might be malicious. And both of these things are modeled by what's called Byzantine processes. And we looked at a technique to model check systems that can handle Byzantine processes. This is called threshold automata. And to keep it very short, threshold automata have limitations regarding long-running algorithms that run in multiple phases, and the number of phases might be parametric again. And the existing tools that have been developed 10 years ago are not supported anymore and or are not very user-friendly. So we developed novel algorithms that support parametric numbers of phases that are based on novel symbolic abstractions related to, again, the BDDs. And we implemented this in our tool Taco. And Taco can now verify multi-phase algorithms, including some things like king consensus and a blockchain consensus protocol. And here's a comparison against existing work. It's also faster on most examples than existing implementations, and can solve some problems that cannot be solved at all before. Okay, then the more high-level approach, where you don't look at Byzantine processes anymore because you assume that this has been already dealt with at a lower level. If you have something that can verify consensus or leader election at the low level, then you can assume to have it at the higher level, and you do it in a single step. And that is what global synchronization protocols do. And then you can, on this level, you can now model more complex applications like distributed stores or distributed robot flocking. And for this, we also did a synthesis approach where you can automatically synthesize correct implementation, but let me not go into detail. And the third direction was systems with time. This is clearly very, very important in distributed protocols, but most of the existing formal approaches do not deal with time. Or if they deal with time, then they do it in a restricted way. In particular, in prior work, time can only restrict the possible actions in the system, but it cannot force an action to happen. But you usually want time to force an action to happen. If a timeout, if you have a timeout and you reach a timeout, then something should happen. So we showed for the first time with a particular communication primitive that we can have, we can support actions being forced, identified a decidable subclass, and even showed that this allows us to simulate other synchronization primitives that are stronger than this, or thought of being stronger than this. But if you add time and you add this property of being able to force actions, then there's actually no difference anymore between the strength of these communication primitives. All right, and here it's the only point where I want to talk about future work. So we have lots of plans in this area, and it can be summarized more or less easily. We want to bring all of this together into one. Currently, these three are separate things, and the vision is to bring them together and to build a tool that allows you to design and verify distributed algorithms that are correct and have all these properties that I talked about. Okay, I think I'll skip over the learning part and get to my final thoughts. So, this was a wild ride, the talk, but also my tenure track. In the talk, I discussed the historical perspective, how formal methods evolved along with the practical requirements, sometimes being in front of the practice, sometimes being behind. But clearly, there's a strong influence between the two. And even though Dijkstra's vision has not been realized, many of the techniques that I talked about have made it into practice, at least in some application areas. Regarding the The second part, my career. I think I'm lucky to be where I am. And I also think that we can all benefit from acknowledging the aspect of luck and chance in our careers. And regarding my research, I said this before, we have produced some very exciting results in information flow verification and in verification and learning of distributed systems. And many interesting challenges still lie ahead. Thank you.